Okay, quiet, quiet. Shh. Okay. Okay, so this is the problem from last week, okay? We're going to hopefully get through all of it today. I might not get through all of it. We're going to finish up tomorrow. We're going to continue on with friction and torque. We're going to do one more quick problem with friction. Actually, we're going to do one more, not quick problem, but an angled block problem so we can deal with an inclined plane. And then we're going to move on to torque, okay?
Yes.
All right. We're going to have a laser cutting project for everybody in torque. We're going to make a mobile of some sort so you can actually physically make something, okay, to do balance and center of gravity. Huh? A what? No. This should be a lot quicker. Yes, sir. No. You guys, where's yours? You were saying no. You can watch it. I want you to watch this. Okay. Turn it in. Okay. I really don't care. Right. My issue is I want you to understand the problem. Okay. So work it with me. And if you get questions, you talk to me. Joe, what's up? I'm still working on the requirements but I'm determining, do you guys want to make your own mobiles or a large class mobile? Okay. We're going to do a large class one then. So you have your own individual pieces that you'll do. All right. You can be the pretty police. Okay. All right. Shh. I just want you guys to know I'm going to miss you guys a lot next year. I really am going to miss you guys.
Yeah, we're having the whole art is right?
It's like, that's why I'm only teaching one class. All right. What?
You're going to miss the total disaster chaos from us?
Be honest, you are.
The disaster, what?
Are you just happy to say shock and awe?
No, I will email you all a shush next year so you have it. All right. Like Randy Malik. Shh. Okay. All right, listen up. Shh.
Can I come visit you at La Jolla?
All of you are more than welcome to visit me in La Jolla. Yes. Okay. All right, now, quiet. Someone explain to me what's happening in this problem. Someone explain it to me.
Pulling a pulley, which has a rope on it that is connected to another pulley, that's connected to a pulley above, that's connected to a fixed pulley that is pulling a rock on the ledge.
Okay. Who wants to add? That's a good start. Who wants to add? Yes. The question is, how much time does he have?
And he named it Joe.
Joe Stickman. Okay. What else, guys? What are we missing? What else is going on in this problem? Nina, what else is going on in the problem? We hear come on, give me some more detail. Some more detail about the rope.
Oh, you have the same tension at all points.
Okay. But where's the rope attached to?
It's attached to the wall and the rock.
Okay, wall and the rock. Now, so as I'm starting to pull the pulley to the left and the bottom, I'm going to start to take up rope, pulling the rope to the right, dragging that rock over to this person's core head, okay? Now, what's the difference between case 1 and case 2? What's the difference between case 1?
Case 1 is trying to get the rock to move, and case 2, the rock is trying to move.
Yeah, in case 1, he's trying to start his death, and then in case 2, he succeeds, right? So case 1, but what is the pure difference though? And the pure difference between case 1 and case 2 is what?
The
Okay, we go from static to kinetic friction. Okay, so
Is it static and dynamic or is it
kinetic. Static and kinetic. So when we talk about static friction, let's say the static friction force is 100 newtons, and the tension on the rope is 100 newtons. What's the rock doing? If the static friction force is 100 newtons and the tension on the rope is 100 newtons, what's the rock doing? Nothing.
It has to be greater.
Your force has to be greater than the friction force, the static friction force, in order to overcome friction. And remember, when we look at the graph, okay, of friction versus time, okay, our friction force goes up linearly, comes down and goes over. Now remember, this means, guys, that if I'm pulling at, let's say the static coefficient of friction, let's say the static friction force is 100 newtons, but the rope has a tension of 50 newtons. What's the static friction force? If the static friction force ends up being 100 newtons, mu, let's say it's mu times F of n is 100 newtons, okay? And I pull with 50 newtons, what's the actual friction force?
It's hard to do this like here. Yeah.
Okay. All right, here's the scenario. All right, ready? Here we go. Here's the example. Give me my rope. Where's my rope? Here's my rope. Okay. I need a volunteer. Come on. Come on up.
But
Okay.
I wanted to do it.
I'm sorry.
That doesn't work.
It does. Stand on this. Okay.
No,
do
it
like
doesn't.
this. Do like this. Like this. Hold tight.
Wait, don't stand on it.
Okay.
Because it'll fall over.
Listen up. Everyone watch this. This is important. I'm doing it visually. Look. Okay. There's a friction, a static friction force that I have to overcome to get him on the slide, correct? Okay, let's just call that 100 newtons. I'm pulling, pull back on me. Am I pulling at 100 newtons?
No.
How about now? No. Okay, but I'm pulling less than 100 newtons. How much, let's say I'm pulling 50. How much is Iman pulling back? 50. So the friction force is always equal to my tension for my pulling force until I overcome. Does that make sense? Okay, thank you very much. That was it.
So wait, the friction force is like the force. No.
It's like exactly because friction.
But it's like the horizontal force.
Exactly.
Because you don't have multiple forces vertical.
Right.
Boom!
And because look, and hey, boom, look. Friction force equals mu times the normal force. Okay. All right. Okay. So. How do we start? And then after it, then what was case 2? What was case 2? What did we say?
How long does it take it to move? 0.5 meters.
Okay, but before we got there, what was the issue in terms of the forces? Talk to me about the forces.
Well, it's moving now, so now you don't have friction force.
How much am I pulling now? How much am I pulling?
More than the friction force.
Okay, whatever. Well, remember we said in case 2, you calculated the pull force for case 1, right? The tension had to be equal to the friction force, which means his pull force is actually twice that. We'll talk about that, why that is in a minute. But I said that in case 2, his pull force is the same pull force from case 1 plus 1 Newton, right? Yeah? Okay. So let's go forward with this. Nothing. All right, so what do I got to do? What's the first thing I got to do?
What is
Usama.
that? Did you do that?
Yes, the printer.
Wait, this is case 1, right?
Case 1. Regardless of the case, what do I got to do first?
Free body diagram.
Free body diagram. And before I do the free body diagram, what do I have to do for the first step of the free body diagram?
Draw your circles. Draw
My-
your circles.
My what?
That's the word for a dotted shape that indicates where you're going to put a free body diagram.
Really? A
I came
dirtle?
up with it.
Oh, okay. I was like, I've never heard of a dirtle before.
You should have made him set
Mr. A, you know, the interviewed us used a dot as a free body diagram.
They
That's
interviewed?
your competition.
They interviewed us? Interviewed you?
They interviewed us.
Oh, today? Uh-huh.
It was like last Thursday.
Oh, yeah. Uh-huh.
He used a dot.
Hey.
I'm trying to say, you get some competition.
Hey. I'm more correct.
Your shape's better.
Thank you very much. Did you tell him that?
I wasn't there. I would have. But like, excuse you, I don't like this. Other shapes.
Okay. What do I have? What? Oh, because he spilled it. All right. So, shh. So let's do our, guys, quiet. Let's do our free body. Let's do our boundary art. What'd you call it? Juliana, what'd you call it?
Jerkle.
Dirkle. Let's draw our dirkles. Where are we going to draw the dirkles around? Hello, Bueller. Where are we going to draw the dirkles around? Where are we going to draw the dirkles around?
Around the things that you're drawing a free body diagram of.
Okay, give me an object.
The rock.
The rock. Okay. All right. What else? What else?
That other pulley up there, and the other one and the other.
Okay, the other pulley there.
And
Okay.
the other one.
And then which one?
That one.
This one. Okay, what else?
Then the other one.
Then the other one. Okay.
And
Anything
that's
else?
it.
Now, I could draw it around the guy, but I know that the pull force out is going to equal to my tension force, or equal to that tension, right? So, because it's a different rope, the pull force coming out, the force coming out to the left of this is still the pull force, right? Everyone got me? Everyone with me there?
Yes.
Ladies? Okay. All right. So let's now draw. Let's draw the forces on each of these let's draw the forces, guys. Shh. Oh, darn it.
What did you do?
I did it in the wrong layer. Hold on.
Oh my goodness.
Gah. Gah. Here we go. All right.
You wasted so much time this grade.
I know. All right. So what are my forces on the rock?
I don't know, Mr. A.
No,
I'm just
well,
kidding.
okay,
Force
well,
normal, force gravity, force normal, force gravity.
Force of gravity down.
Force friction.
Yeah, there's the normal
Force
force
tension.
going up.
Tension.
There's a
normal,
force of gravity
force-
going down.
There's the normal
tension.
force going
Slow
up.
down.
Normal force.
I'm sorry that I'm just on different pace than everyone else.
There's the T going towards the right.
The what?
The T. And then there's the force of friction going towards the left.
Okay, there's a force of friction going to the left. Now, is it static or dynamic?
Right now. Wait, is it moving or not?
Okay, both of them will go to the left, right? Both of them will go opposite from what you're pulling. So depending on which case, but they're both going to go that way. Okay?
I like how you casually just have these things sitting around. I could just like write Tina right now. Honestly.
And then it's recorded, and we know we will give that to the police. Okay, next scenario. What is the next? Where are my forces? What are my forces on the top right pulley?
You need the force of the bracket up and right.
Okay, so there's an F, B, Y, and
Yeah.
okay.
Maybe not the force of that done thing that's at an angle, with the rope at an angle.
Wait, before we do the angle,
It's the T.
okay, what?
You have a T going down.
Okay.
And you have a T going at the angle, but you have to break that up into X and Y.
Okay, because when you put the force on the free body diagram, you've got to do it at an angle, right? So it's T, Y, and TX. Everyone with me? Because there's still a rope over here. You see, there's two ropes. These two T's represent this tension here. Alexa, do you see that? And then there's another tension coming down.
I have a question.
Yeah,
If you know,
I don't.
well, you know that the tension in that rope is the same tension as the other one because you said the tension.
What other one? What other one?
You know the tension right there is the same as the tension right here, right?
Wait, the
That's how you
tension
find-
here. The
that's how you
tension
find
here
the
is the same.
TY.
Yeah, but this tension, part of it goes down, part of it goes up, or goes to the side. Excuse me. Part goes down, part goes to the side. So not all of this rope tension pulls down.
Oh, so
Wait,
you can't
you
do
gave us
FY.
the degree, right?
What?
Did you give us the degree?
I did 55 degrees.
So like the reason you guys put summations.
Yes, because you can't summon an angle. You got right. Okay. All right.
I'm paying attention.
Thank you.
I'm paying attention to obviously, and that's one of the questions.
Huh? Good. How many have got? Okay. So now, the on this pulley here, what are my? Actually, let's do this one here. On this one here, what are my forces here?
2T towards the right.
Okay, I've got T and I have T, and what?
You have the force of pull to the left.
The force of the pull to the left. Now, what I'm going to do, just to help me sort of clear some things out, I'm just going to sort of move this out of the way, down to here. All right. Now, on this guy, what are my forces on this guy here?
Wait.
On this pulley right here.
You have up T, left T, down.
But actually, hold on one second. At this point, everyone, Sam, at this point, what are these arrows showing me and telling me about this box?
The
That
direction.
is going up and left.
That the box is staying still? If I look at just this diagram alone, it says it's moving up and to the left. It's accelerating up and to the left. right? Because I have unequal balanced forces, unbalanced forces. You see that? So in order to, but if I know it's standing still, that means I've got to have some other forces, right? I've got to have a force both downward and to the side. Osama, where is my force on this guy, kiddo?
To the right.
Which, to the right? Okay, what's happening? What's it called, Osama? FB2X. Osama, what's my other force I'm missing?
Down.
Okay. And what are you going to call that? What physical object is creating that downward force? What physical object? Which one was creating this FB2X? If I look at this, guys, right? If I bring this back up, okay? In this scenario, an FB2X, what physical object is creating that force? Not the wall.
The bracket.
The bracket. It will get transferred to the wall. Okay? It's not. Who said it's the same thing?
Yeah, actually, what is
It's
holding
not-
that down?
Okay. What is keeping this down? Usama. Usama.
But which bracket?
Yes. The same brackets.
Oh, yeah.
Okay, and we're gonna get in. What's actually happening is we're creating a moment. We're creating a
If it's like hard, I can't pull it up.
right, but it's trying to bend it around this point right here. So we're actually creating, guys, a moment arm. When we get into torques tomorrow, we're going to talk about that. Okay? All right? Okay. So now I'm going to call this one, Usama, what? What am I going to call this force? Kiddo.
Force the, Matt said it.
I know he said it. I can hear him. Matt thinks he's quiet, but he's not. Usama, I need you to pay attention and stop whatever you're doing. Where's your paper, sir? Where's your paper? Where is it? Wait. It's at home?
It's up your district.
Okay, hold on.
I wasn't
Stop.
here on Friday, so I couldn't.
No one was here on Friday, sir. Usama, I received no email. When I receive, yours is now an incomplete. When I receive it tomorrow, maybe, then it will be 10 points off. Because it will be late. Is that clear?
You're very generous. Yeah, seriously. That's why I give you 90. That's why you don't check their grade at all.
All right, I'm giving you 50 points off.
My other classes is like half off.
I would give you guys a 0,
Well, no, it's
but
not. The only reason it's worse than other classes is because like this is automatic 100 if you turn it in, which means if you're late, it's 10 points off. Usually other classes you get like a 90 anyway, so 10 points off would be 80, which is like a big deal. Miss Sellers is so good.
I technically, you guys all signed a 0 to be turned in late. Okay. All I'm saying is that I'm gonna make it up. I'm making it up on the next test. That's all I'm gonna say.
Kind of motivating, actually.
Yeah. Demotivating or motivating?
Motivating.
Mine?
And it's 0.
Yeah.
It's like, unless it's actually like a legitimate reason why like you couldn't. And it actually,
Technically, it is.
Like, well, like if you were actually absent,
Uh-huh.
yeah, you like have zeros as a filler. But like you put in a 0 for mine, but it wasn't weighted, so it was like fine because it didn't bring my grade down. Just saying.
All I care about, guys, is you understand the material. That's my goal. Okay.
I get it. It's just like when you see those random things, it's like what the heck? Like once I get
Can we
stuck in
finish?
my head-
Yeah, let's finish.
Oh yeah. Sorry.
Okay, so let's move along. Shh. Okay, so now I have my. Why in the heck do I draw these free body diagrams anyway?
To know what forces are acting on it.
I'm sorry?
To know what forces are acting on it.
Yeah, to account for all of my forces, so that I can then do what?
Summate. Is that a word?
Yeah, I can sum. I can create a sum and essentially an equation, right?
Like summation, like you can summate.
Yes. Okay, so I can now create an equation that models my forces, correct? Okay, so, all right, so for the first, let's look at number 1, free body diagram 1. This is for my rock. Wait, what is this for? This is actually for my,
That's for your rock.
no, that's for my upper right pulley, because it's TYTX, right? So how many directions of force do I have?
2.
two directions of force. I have forces in the x direction and forces in the y direction. I asked that question, misleading as it is, so that I know how many equations to write. Does that make sense?
You only have two, though, shouldn't you?
Well, some people some people might say, well, I have one up and one. I have two here, then two there, so it's four directions. I get that. I get why they say it.
Stupid people.
No, I'm just no. Andy. So the sum of the forces. Yes, ma'am.
You're not gonna make us do a three-dimensional one of these, are you?
Oh my god.
No, I would. That would be cruel. That's not.
Not because we wouldn't understand it, but because
Yeah. But by the way, in freshman engineering, freshman engineering, you will do those kinds of things. I had to do those. Yeah, it's actually not bad. If you can do this, you can do three-dimensional. It really isn't hard. It really isn't hard. It's actually kind of fun and
Scintillating.
no, like Zen. You're kind of it's therapeutic. Chilling. Just kind of get done. So some of the forces in the y direction. What are my forces I'm summing up? Tell me what they are. Ram, what are they?
Alright, so we've got our force of gravity on the bottom. There we
Whoa. Look at my free body diagram. What force do I have in the y?
Alright,
TY.
I don't have my contacts.
FBY. What else do I have? T and what? TY. What is it? What thing does that equal? What thing does it equal? What kind of thing does it equal? Net force. It equals a net force. A net force. Okay? That force, if my pulley is not moving, then that net force equals 0. Okay, that's okay. No, you don't. No,
I just wrote 0.
that's fine. That's fine. But I want you to, I'm kind of hitting this point home because I want to make sure, because force equals what?
Mass times acceleration.
Mass times acceleration. Okay, and that was too easy. You got to answer a hard one. So acceleration, if I have a mass, then my acceleration must be 0 if I'm not moving, and therefore my total net force is 0. Because in the case of this rock, okay, in the case of this rock here, this rock will eventually have an acceleration to it, won't it? Okay, so we'll have a net force that's non-zero. Okay, so sum of the forces in the x direction, what are those forces we're summing up? Someone tell me. Andy Bell, what are those forces in the x direction for this?
TX and then FBX.
Okay, that equals what kind of a thing? Thank you very much. And that net force equals what? 0. Beautiful. Okay. All right, now, let's go to the next one. Notice everything's with variables. No numbers whatsoever yet, right? This is how you guys need to do this on the exam. Some of the forces in the what? How many directions of force do I have in the next one? 2, right? So let's do f of y again. F of y, what are my forces in the y?
I also have a question.
Yes.
On the exam, on every single our T and F, do we have to have units on every single one of those?
No. Like I'm gonna require you to make sure that whatever you equal in the end has units in it. Okay.
Okay.
Okay. But your signs need to be there. Your signs need to be there.
Yeah, I understand the signs, but
Yeah.
units don't have to be there.
Internally, no. At this point, we're just adding up newtons. It's fine. But okay, so some of the forces in the y. What are my y forces? Joe, what are my y forces?
Y forces are T and O.
Guys, you're not paying attention. Hence why I call on you. Joe, I'm working on this guy right here. What are my forces in the y? None?
Which one are you?
This right here. Right here. Joe, don't blame me for you not paying attention. Don't blame me for that. You're not looking. Right here. Right here. Right here. What are my forces in the y?
Now I see it. You're moving, but you didn't show it. You weren't moving.
I was doing it. Go. Tell me.
Okay, F, G, and F, N.
Guys, take ownership. Just say, I'm sorry, Mr. A, I wasn't paying attention. It won't happen again.
No, I already said that when
Say it. I want to hear it. Say it.
If you didn't hear it, it's because you weren't paying attention.
Say it. Say it.
No, you can have a candy bar. That was good. Honestly, that was good.
That was not good. He did not say it. Okay. Shh. So equals my net force. Equals 0. All right. Then
Drives are not the way to get stuff done.
you haven't lived in the real world. Fx, sum of the forces in the x direction. What are the sum of the forces in the what are my forces? Fr plus T equals at net force. We don't know this is equal to 0 yet. We're going to make that two different cases. Case 1 is going to equal 0. Case 2 will not equal 0. Okay. Okay, now this one down below. What are my forces? Matt, please put that up. Now, 3, 2, put it up. Put it up. Up on the board. Now, Matt. You're wasting everyone's time, Matt. Just put it up on the board. Nope, all the way on the board. Matt, put it on the board. Matt, you're wasting everyone's time. Get up, please, and put it on the board. It's a very simple task. Have a seat, Matt. Okay, some of the forces.
Matt knows what he's doing in this class, though. I will say that.
That's okay, but he's distracting everybody else, and including me. Okay? Some of the forces in the x. What are my forces in the x?
T.
Thank you.
SB2X.
Okay. That's going to equal my net force, right?
C.
And this is going to be, this is my bottom right pulley, isn't it? What pulley is this one? Yeah, it's my bottom right pulley. Okay? So that's going to equal 0, right? Some of the forces in the x direction, oh, that's sorry, that was x, excuse me. In the y direction, some of the forces in the y direction equals what?
T plus F sub B 2y.
Okay. Net force equals 0. Okay. All right. So now, oh, we've got one more force. We have one more equation. What's the equation up here, guys? Equation over here, guys. The last one. 2.
Some of the forces in the x, some of the forces is FP and 2T.
Some of the forces in the x is going to equal Fp plus 2T.
Equals FN equals 0.
F net equals 0, right? Okay.
And it's not moving.
If it's not moving. Correct. Now, in this case, what is the only thing that we know? It's the only value that we know
Mass of the thing.
of the rock, right? We know the mass of the rock. So the mass of the rock equals what? What's the mass of the rock, guys?
120.
120 what? Kilograms. So the force of the rock, the force of gravity of the rock, or the weight, is equal to what? Everybody? What's that number? What's the weight of the rock? 120 times 9.81. It's 1177. Correct. Negative 1177. So the weight is equal to negative 1177 newtons. Right? Everyone with me? Guys? Yes? Okay. So where can I use this? Where can I use this? Where can I use this? This weight. The second free body diagram, the y equation, right? So 0 is going to equal my negative 1177 newtons plus Fn. That means Fn equals 1177 newtons, right? Okay. Why do I care about the normal force? What's it going to do for us?
Friction.
Beautiful. Friction force. Because friction force is equal to what? Mu times Fn, right? Okay. So our mu, and is that for static or kinetic? Is that for static or kinetic? Joe, what are you doing? Put the laptop away.
I mean, this has been, I was laughing at the tensions, Joe.
What? So is this for static or kinetic, guys? Is this is for static, guys. Static or thank you. Okay. So what is my friction? So in case 1, we're looking at which friction force? We're looking for static. So the friction force of static uses a static coefficient. So friction force static equals 0. What? In this case, guys. Do you guys remember? 0.8 times my normal force, which is 1177 newtons. So my friction static is equal to what? Is 942, roughly. Correct. Where's my... So my friction force is negative 942 newtons. Right? Everyone with me? Why is it negative?
Because it's pulling that to the
Pulling to the left, exactly. Okay. Now, can I use this anywhere? Can I use this anywhere?
Yes.
Where, Matt?
Yes.
Put it against the. Put it on your diagram.
Okay, in the sum of the forces of the x on diagram 2, I've got Fr plus T equals F net. Now, case 1, is everything static or moving? Static. Therefore, my net force for case 1 is going to equal 0. So that way, my friction force, which is negative 942 newtons, plus T equals 0. Therefore, T equals obviously 942 newtons. Right? Okay. Now, from that T, I can figure out all my other forces, right? FB2x is going to be negative or positive 942. Everybody? What direction is FB2x going? Right or left?
Right.
Right, so it's what?
Positive.
Positive. So it's positive 942 newtons. You guys see where I'm getting that? Okay, what about FB2y? FB2y, what is it? Is it positive?
Wait, where is it? Oh, right there. Oh,
Negative 942 newtons. Okay. Now, okay, the next thing I got to deal with is FBX and FBY. How do I figure that out? What do I got to do first? Got to do some trig, right? So I got to come over here and I got to say, okay, here's my tension, right? Here's my tension. Here's my tension here. So here's my Ty and here's my Tx, right? So T sub x is equal to what? What's T sub x equal to, guys? Quick equation, T times what?
T cosine.
You out of here? T times cosine 55. T sub y is equal to what? T sine 55. Do you guys have numbers for those numbers? Yes. Ty is T sine 55. 55 is this direction. So its sine is opposite. Okay? Okay. It's all right. Okay. So what was the value of T sub y, guys? What was the value of T sub y? Someone has the answer. Anybody? Am I going to have to calculate it? So 55 sine times what, 942? Hello? Okay, so T sub y is next. So T sub y, I'm going to erase this over here. So T sub y is equal to negative 771 newtons, roughly. What's T sub x?
Negative 540.
Not negative. Oh, you're right. No, it is negative. I'm sorry. It's negative 540. Is that right? Does everyone agree with 540? Everyone? Okay. So now we can figure out the rest of this. So FBY plus RT, which is in this formula, what's T, negative or positive? What's T, negative or positive? In this free body diagram. What direction is T going? Down or up or left or right? Down. So what sign is it? negative 942 newtons plus a negative 771, right? Negative 771 newtons, right? So that means if it's equaling to 0, then my FBY is what? (771) plus 942 is 1713. 1713, right? You guys with me? Okay. All right. So T sub x was T sub x. T sub x is negative 540, right? Plus FBX equals 0. So FBX is equal to 540. Okay? Newtons. All right? All right. Did we solve everything? We solved everything for this, right? Oh, we didn't figure out our pull force. And our pull force, I know, is equal to 2 times our tension. So our pull force is what? 942 times 2, right? Is that right? So 1884? Is that right? Is that right?
Yeah.
Hello? Okay. All right. So we have 5 more minutes or 7 more minutes. Let's deal with case 2. What's going on in case 2?
You have to figure out the time. But the thing is actually going to start moving, and you have to figure out the time for it to move a certain distance.
Okay, why is it going to start to move? Because
he's pulling more than the net force, so the force friction.
okay, so let's come over to here for 1 second. Let's take this guy right here, okay? And let's place him over here. Here's my free body diagram for that, right? I'm going to come back. I'm also going to grab one more free body diagram. I'm going to grab this guy here. So I'm going to grab the 2 free body diagrams. One is the one that shows the rock with the tension. The other one's the tension and the pull force, right? Okay. So I said that the rock is moving. So that means what kind of friction are we in? So friction kinetic equals mu kinetic times the normal force. Okay, what was our normal force, guys?
Oh, negative
1172. Is that right? 1177. 1177. So 0.6 was our mu k times 1177 newtons. So our friction force kinetic is equal to what? 1177 times clear. 1177 times 0.6 is 706. Okay? So we've got 706 newtons. Okay? And that's negative, right? Okay. Now, I said that in this case, his F of P, okay, was equal to what? F of P case 1 plus 1 Newton. So that means it's what? 1885. 1884 plus 1. So it's equal to 1884 plus 1. So F pull is equal to 1885. Right? So if we look at this guy here, we said the sum of the forces in P is equal to, the sum of the forces on the X, here, equal to F of P plus 2T, okay? And we're going to look at that initial case, right? When it's 0, we're going to say F of P is equal to the opposite of 2T, which is negative 1885 times 2, right? Oh, I'm sorry, excuse me. Take that back. So 1885 negative equals 2t, or plus 2t equals 0. So t equals 1885 divided by 2 is, that's not right, 1885 divided by 2 is 942. So is 942 newtons, right? Yes? Okay. And now we know that the sum of the forces in the y direction is equal to 1885 oh, excuse me, 706, negative 706, okay, plus 942, which is equal to what? 200 and, I can't do that, man. Anyone? 36. What was it, 942? No, what is it? 942, 706. 942 minus 706. Yeah, 236, thank you. So 236 newtons positive.
That's the F of X, right?
X, I'm sorry, excuse me. Equals our F net. So that's our force net. That means we're accelerating, aren't we? How much are we accelerating now? How much are we accelerating? How do we determine that?
You can do that minus force friction. Oh wait, no.
We just did that. Okay, so 236 newtons equals mass times acceleration.
Mass is 120.
Right, so acceleration is equal to 236 newtons divided by 120 kilograms, which is equal to what, guys? So 236 divided by 120 is 1.97. 1.97 meters per second squared. Okay, everyone with me? Okay, so now the question is, how fast is he going, right? Let's look, or how long does it take for it to move? Let's do this. So I come over to here and I say, all right, I'm going to snag this right here. I'm just going to copy this. I'm going to add a new layer. Okay, here we go. And our acceleration is what? Acceleration is 1.97 meters per second squared. Okay? He's got a half a meter to go before he starts to fall. We're looking for time now, right? All right, so you guys figure the rest from here? We'll finish it off tomorrow? Okay. All right.